Okay, we're going to talk about this really quick because we will see it in other problems in this chapter. So this is the activity of the species formula, and you can see that activity is A sub C, and that is equal to the concentration of your formula times the activity coefficient. Now there's two ways to find the activity coefficient. You can work this formula. Please do not work this formula. For the love of God and everything that is holy, do not work this formula. It gives me math anxiety just looking at it. The easier way to do that is to look at table 8-1 in the Harris textbook. If you do not have the textbook, you don't have access to this table, please let me know. I will send you a screenshot. I will send you a picture. I will print you out a copy. Just don't try that. I mean, you can if you have to in a pinch, but man, that's not work. So this is one of the questions from the practice quizzes for the material that we covered last week with activity coefficients. I would not be surprised to see this on the next exam. Okay, so it says, what are the activity coefficients for lead 2+ and I- minus in a solution with an ionic strength of 0.01? Okay, so we're going to look at table 8-1, and this is very important why you need to have this table. Okay, if you don't have it, let me know. So we're going to find lead in the plus or minus 2 section here. So here is lead 2+, and we're going to trace over until we get to the 0.01. And so that value is 0.665, and then we're going to do the same thing with I-, which is here. And then we're going to come over to the 0.01 and see that that's 0.899. The thing that I wanted to point out here is you cannot solve the rest of the equation without these two values. So it's very important to have this table because I doubt he's going to give us these values. Okay, the next question on this quiz asks, what is the equilibrium constant considering the activity? All right, and we are going to need to answer that question this equation right here, the thermodynamic equilibrium constant. So Ksp is going to equal the activity of each of the ions in there. Okay, so you're going to have your concentration times your activity coefficients for each. So this, what I've got on here is for calcium sulfate, but we're just going to sub in our lead iodide into this formula, and we're going to get our answer. Well, I have went ahead and plugged in our values. So the question gives us our Ksp, and we know that we're going to have to use the thermodynamic activity equation. So I wrote that down here, and then I plugged in our values. So our Ksp is equal to 2.8 times 10 to the negative 18. And we're going to set that equal to the concentration of our lead times its activity coefficient, okay, times the concentration of iodide squared, because there's two. You look at our equation, there's two iodides, times its activity squared. Okay, I got our numbers in here. And then in order for us to move over the activity constants, we have to divide this side by them because they're being multiplied up here, and then divide this side by it. So we've got 2.8 times 10 to the negative 18 divided by that should say 665 there, and 0.889 squared. That's going to give you an answer of 5.209 times 10 to the negative 18. It's going to be equal to our lead 2+ times our iodide concentrations. Okay, and the iodide is still squared. We do not have to go further than this because we're not looking for an actual value for the concentrations. We're just looking for the Ksp expression. So that is how you solve that equation.